remember the dy dx, that's just going to give us our slope. So we've done these before with the hash marks here. So what helps me on these problems, you don't necessarily need to do this step, but it helps me to write the coordinates down of each of those points that they give me. And I just take those points and plug those in place for the x and the y. So I'll take the -1, plug it in for the x, take the 0, plug it in for the y, and then there's my slope is the -2. And I'll do that for each point. So down here, I'll take the 1, plug it in for the x, take the 2, plug it in there for the y, and then there's my slope for at that particular point. And then it's all relative. So if my slope is 0 at a point, I'll make that a horizontal hash mark there. And then I got 1, 2, 3s, and 4s. So if the slope is 1, I'll make that like the least steep line. If the slope is 2, I'll make that a little bit steeper. If the slope is 3 or 4, I'll make that the steeper ones there. So it's all relative. To just make a slope of 4 a little bit steeper than the slope of 3, and we should be good on those. And then once you get your hash mark, sometimes that's all they have us do. And then this one also want us to sketch the solution curve that passes through the point there. So you're supposed to just look at the way those curves are going. See, they're kind of going in that direction, and then just kind of just draw a little curve real quick there. It's typically not worth a lot of points when you have to draw that curve, but it does say go through the 0.01. And then so I just kind of did that. And so we'll see a couple more of those in the future as well. Now, when we move on to part B, it says you got a local min, right? So we know at the local max or local min, that's the same thing as a relative max and a relative min. We know the derivative is equal to 0 there. So when they're talking about what's the y coordinate of this local min, they give us the x value. All I know is when I see max or min, that means I'm going to take that derivative and set that equal to 0. So they gave us the derivative, I set it equal to 0. They asked me for the y coordinate, so I solved that for the y, and then they told us at x equals ln of 3 over 2. So I just simply plugged it in for the x, and there's our y value right there. So when you see max or min, set the first derivative equal to 0. If you start seeing inflection points, you know that's involved in that second derivative there. Letter C, I like letter C. This is like our first time we're seeing this Euler's method there. Now, anytime I have seen the Euler's method on the AP test, it has been pretty much identical looking to the process I showed you in the BC Extra video lectures right there. So watch that again if you need to. This is on the no calculator part of the test. So sometimes I'll change the decimals to fractions because the fractions are a little bit easier to work with. Sometimes if the decimals are small enough, I'll just leave them as decimals. But very, very similar to that short video for the Euler's method, right? So just practice this without the calculator. So it says we're starting at x equals 0. And then 2 equal sizes to get to f of -0.4. So 2 equal steps, that means the delta x has to be this -0.2. So I go 0, -0.2, -0.4, and they want to know what is that y value right there. So I'm just going to do Euler's method a couple times, and whatever I get right here, that will be my answer. And so here's our starting point. They told us to start at 0, 1. And then remember, it goes delta y and then your new y. Your delta y is delta x times the dy dx. So I'm going to take -0.2. And then the dy dx means I got to take the 0 and the 1, take those and plug those in place for the x and y into that first derivative right there. So I'll go 0 minus 1 is just going to be a -1. So if I go -0.2 times a -1, that's where I'm getting this positive 0.2 at. And then all you got to do to get this number is add up these two numbers here to get that 1.2. And then that is your new y value. And then you repeat that process. And then typically that next time it gets a little bit more involved because you have more decimals and stuff in there. So what I'm going to do is I got to take delta x times the dy dx. So I'll take the -0.2. That's why I wrote this down here. There's my delta x is the -0.2. And then for the dy dx part, I got to take this -0.2 and the 1.2, plug it in for the x and the y into that first derivative right there. And so that's what I'm showing right here. Then I did some arithmetic, did some old school multiplication to get that was 0.32. And then I added those up right there. I even tried to be extra cautious and add those up properly down here. There's my 1.52, and that's our final answer for that. In the future, I think what I do most of these problems is I'll convert like the 0.2 to the 1/5, and I'll usually convert everything to fractions because I found that sometimes my brain isn't as accurate with the decimals as they are with the fractions right there and getting common denominator. So at least we have the option, but they usually keep that pretty darn doable without the calculator. So we'll be perfect with Euler's method. Like in the future, next time you see that, you'll probably knock that out, no problem there. You know, Taylor polynomial is going to take a little while, parametric polar going to take a little while, but Euler's method, we should have that down like right now. All right, and then the tricky part, so I mean, A through C, we're going to have down with some practice. Part D was pretty tricky as far as knowing what I was supposed to do. There's two parts to part D. The first part we can be fine with. The second part was pretty tricky to know, oh yeah, that's what I was supposed to do right there. So I'll explain it to you. It'll make sense. And then sometimes we'll get those things and sometimes we won't. But A through C will have perfectly. And then the first part of part D will also have perfectly, just with the effort alone going through these problems here. We know that means the second derivative. And so here's our first derivative. So I'm just going to do a straight derivative. Derivative 2x is 2. The derivative of y is just like 1. But if you do derivative of y, remember you're supposed to tag on a y prime or a dy dx. So here's our second derivative. But then notice it says in terms of x and y, which means it doesn't want the y prime in there. You have to get rid of the y prime. And the way we're going to do that is just substitute the dy dx in right there. And so you can distribute the negative if you want, or you can just kind of leave it like that. But that's the first part that is done. So we can at least get that part. And then you probably came to this video because you were struggling when you didn't know what the heck to do for that second part there. So here's what went through my thought process. At first, I had no clue what I was supposed to do either. And then I thought, okay, what do we use the second derivative for? We use the second derivative for concavity, okay? Concave up, concave down. And so then it's talking about this f of negative 0.4. So when I looked at negative 0.4, negative 0.4 is in this region here in the second quadrant. Now, as I look in that second quadrant, I noticed that all of these slopes, these hash marks, were negative. Now, if the slopes are negative, that means my first derivative is going to be a negative. So when I have this 2 minus dy dx right here, the dy dx in that second quadrant where we're looking at that x equals negative 0.4 is going to be a negative number. So negative slope, that's a negative number. So when you have 2 minus a negative number, that's going to turn into 2 plus a positive number, and that's always going to be positive. So that tells us the second derivative is always positive. And then that tells us that the original curve is always going to be concave up, right? So that was pretty darn tricky. And then, so what does that mean for us? Okay, so you'll see this next concept in the future as well. If we could determine that the second derivative is concave up, they're asking, is the answer that we found in part C greater than or less than the actual y value? Now, when you're using the Euler's method, sometimes you're using the equation of the tangent line, the tangent line approximation stuff right there. Here's how you can tell if it's an under or overestimate. The reason this is an underestimate right there is because if we know the curve is concave up, that's what we found with that second derivative is positive, the curve is concave up. You realize all of the tangent lines that we draw, like if that's x equals negative 0.4, all the tangent lines that we draw there or there, wherever the tangent lines are actually below the actual curve, right? So here's a point on your actual curve. And then here's a point on your tangent line that you're getting like using the Euler's method technique there, or the equation of a tangent line. There's a point on your tangent line, but your actual point on your curve is actually above there. So that's why we use that second derivative in the concavity to try and determine whether that's an under or overestimate. So your point is actually on your curve up there, and then as concave up is going in there. And then the flip side would be true, like if your curve would have been concave down, then your tangent lines are above. So all your Euler's method and your tangent line approximations will be overestimate because your point will be there, but your actual curve point will be right there. So that's why when I realized it was concave up, and then I knew the tangent lines were below the curve, the answer you got is smaller, it's below the actual answer on the actual curve right there. Banana.